This is Lecture 1, Part 2. So in Lecture 1, or Part 1, we did the argument case for the instrumental analysis, namely as a enhancement or extension of our sensory capabilities. And the phenomena are pretty much the same. For example, the conversion of light into an electrical event, namely the events that occur in the retina. In the case of an instrument, you create a voltage or a current accordingly. So the processes are electrification, namely the formation of an electrical potential, and then passive devices that respond to the electrification, namely resistance, which is linear, and or capacitance and inductance, which is nonlinear. I introduced transducers and sensors, the distinction being that the transducer is something that converts energy, the sensor is something that responds and causes a change in the overall balance of the system. A voltage source is something that generates electromotive force, namely creates a potential to push charged particles through a circuit. Voltage is equivalent to potential energy. And we have the symbology of the device itself, namely these parallel bars or uneven parallel bars with a positive sign indicating the region of the high potential. If you go to a book and don't see the little plus sign, then the bar that's largest corresponds to the high potential side. Okay, so the current is treated hydrodynamically. So we imagine a flow of charged particles through a material that's defined as the current. The velocity is affected by a resistance. So there's something akin to friction through the system. And there's often referred to as a flux number, namely the number of coulombs per unit of time. The resistance is a drag, generates heat, so analogous to mechanical friction, you generate heat as the current flows through material and is slowed down. The overarching or the principal equation used to describe this phenomena, the relationship between the electromotive force, the voltage, and the current that flows through it and the material itself is Ohm's law. So the impedance is the same definition largely as the resistance, except that you include capacitive and inductive contributions, nonlinear in other words. So in the case of impedance, you replace, or the Ohm's law of impedance, you replace the R representing the resistance with Z. So the units are volts, amperes, and ohms. And in the case of the AC, the nonlinear systems, impedance becomes Z. So now if we look at resistance, the first of the properties of materials that we're going to discuss, it is expressed in terms of units, ohms, and SI units. As you observe a given object, however, you find that the bulk properties, in other words, the resistance of a material increases with its length and it decreases with the cross-sectional area. So again, think of a rectangular block and voltage applied across the narrow ends of the rectangular block. As the block gets longer, the resistance goes up, or the measured resistance would go up, the current would go down, obviously. And as you increase the cross-sectional area, the current would go up, and so the resistance would go down. So because of the dimensional aspect of this, one refers to a specific resistance, analogous to specific gravity or density, or specific heat. And the units of specific resistance are ohms centimeters. So when you multiply by the length and then divide by the cross-sectional area, you get the resistance of the material. When you build these things, you can take a section of wire and wrap it around a form and this will be called a wire wound resistor. It has its benefits, it has its drawbacks. We'll talk about those later. Or a composite material, so you can fill, say, a cardboard tube with a an insulating material like graphite and create a resistor that way. So carbon composition resistors would be essentially a little tiny can containing graphite. The symbol that one typically uses is the Charlie Brown stripe, and we'll use this consistently through the course. So here's a wire wound resistor from my laboratory. It is a ceramic tube around which is wrapped a rather nasty looking piece of metal, and the zigzag that you see under the green epoxy coating is the wire. You'll notice that the wire is tapped. In other words, there's a connection you can make at certain points along the winding, and you can take sections of the wire and create different resistors based on the positions between two taps. So for example, I have one turn of wire here, I have one turn of wire there, I have 3 turns of wire between this I guess a third and the fourth tap. I have 5 turns of wire between the fourth and the fifth tap, and I have another 5 turns in the resistor. So I want to demonstrate here the meaning between open and closed circuit. So I have a voltage source, or a source of electrical potential, electromotive force. When it's sitting around doing nothing, like a battery in space, it's not going to discharge. A battery over time, if you want to get down to the nitty-gritty, will eventually degrade over many years because of collisional encounters between air particles and the battery surface. Some of the electrons will escape as a result, but this is slow on the normal daily time scale. So if we talk about an open circuit, there's a connection, but there's no complete circuit connecting the high potential side of the source to the low potential source. I want to, however, in a morbid way, explain to you how live wires or open circuits can become dangerous. It's relevant to working in the laboratory. So, a dangling wire attached to the high potential side of a source, it would be considered a live wire. If you happen to wander into the presence of a live wire and touch the said live wire, you are going to complete a circuit to the ground, namely the other end of the potential source, if you happen to be, that happens to be a grounded circuit. As a result, the current will start to flow through your heart, contracting the heart, causing either damage or potentially death, depending on the magnitude of the current. Very morbid. Okay, by comparison, we have what are called closed circuits, where you make a complete loop connecting the high and the low end of the potential source. So again, as in the previous little morbid demonstration, your body can potentially become the closing of the circuit. When I draw circuits, I'm going to use a cartoon fashion, and I'm going to try to minimize the amount of space I occupy on these slides and in general drawings on the blackboard, largely due to the limitations in the tools I have available, the graphic tools in PowerPoint. Anyway, so the symbols should be obvious: the Charlie Brown stripe for the resistor, the uneven bars as the voltage source. I want to indicate that how I connect elements in a circuit is by heavy lines, but they're unadorned. There's no symbology to them. So I have the discrete valued resistor. I have a connection. In effect, this is a wire. It doesn't have to have the shape indicated, but it signifies zero resistance, or resistance that's insignificant in terms of the operation of the circuit. Obviously, if it's a sectional copper wire, it does have a specific resistivity, but the resistivity is so low, it is, in effect, zero as far as the circuit is concerned. I'm going to have a current and the current will always flow from plus to minus in the direction I just indicated. The electrons, bear in mind now that due to historical reasons, current was thought to be a positively charged particle, and so the direction reflects the flow from high to low potential. In actuality, the electrons go from the opposite direction. Those of you who've taken quant are familiar with this through our discussions of a galvanic cell. The load is a term that I'm going to use this term to refer to whatever is connected to a power source. So in this case, I have a single resistor attached to the power source. I would claim that this is a resistive load. If I have a system that contains inductors and capacitors, I would have to kind of scooch the definition, but it would be an impedance load. So a little nuance and referencing to some previous slides in parts 1 and in this part. The voltage source has some internal workings. We don't really care right now how they work, but as a result, the device has a positive potential and a negative potential. A separation of charge would cause a voltage difference. But remember, or at least keep it in the back of your mind, that the potential as defined here is analogous to the definition of potential energy in mechanics. There's no reference here defined. We can only define the potential from one point to the next. So we would claim that the voltage is the difference in potential between these two points. Okay? Now, if we go along the circuit, we have a section of, in effect, zero resistance, namely the top horizontal part. So that if I were to measure the potential, since this resistance is zero, the potential is the same as I go along that section of conductor. Similarly, the potential is the same along that lower conductor. So the fact that there is wire connecting the source and the resistor, and as long as the wire has a very low resistance, then the potential is the same throughout that region. The only time you start to see a change in the potential is across a device that dissipates energy. So the resistor, as the charged particles go through it, the resistor causes friction and you lose energy as heat, thermal energy. So you claim that there is a voltage drop across that resistor, and that's what you measure. So when you measure the voltage difference, you'll see that dissipated across the resistor. We'll get into this in a little more detail shortly. I want to introduce, or at least talk about, Ohm's law and circuits using another physiological example, and also incorporate a little bit of safety discussion into the lecture as well. So if I hold a battery between my forefinger and thumb, I form a circuit, right? I have that. If I look at some physiological measurements of resistance, and this can be found in the Van Dijk book, tissue is essentially an electrolyte solution, 7% salt roughly, has a resistance of about 200 ohms. Skin is what saves you. It's dead tissue. The epidermis has a 5,000 ohm resistance. So if I were to calculate the resistance of that fingertip circuit, I would take 5,000 ohms, add 200, add another 5,000 for the skin between the thumb and the anode of the battery, get a total of 10 kiloohms, 10.2 kiloohms. If I look at the voltage of the battery itself, a 1.5 volt battery, and apply Ohm's law, I get a resultant current of about 1.15 milliamps, which is nothing really, it's minuscule. If I apply the same to a 5 volt battery, I get half a milliamp, still not too bad. Not going to really feel like that. I get to 10 volts, and I'm starting to get to a range where I might start to feel things. Certainly when I get to 100 volts, I have 10 milliamps, and that's approaching damage level. So you can see that depending on the voltage source, you can run into danger. Regarding the damage, the power is defined as the current multiplied by the difference in the voltage. So I can get a significant amount of power being dissipated by me, or dissipated through me, in the form of heat. So what happens to you in the case of electrocution is you get cooked. And you can compare this to, say, a hot plate's power rating. So you see birds on wires all the time, and you wonder why they don't drop dead or get cooked immediately as well. So the issue in the case of the bird and squirrels as well, they form a parallel circuit. So their feet make contact. The resistance is actually external to the circuit, so that when the current starts to flow, it bypasses the void and doesn't fry them. So there's a certain advantage depending on how you hook yourself up to the system. Again, I have a very colorful story regarding my own gripping of a high voltage light source, and rather conveniently, well, nearly killing myself is essentially the story, the short version of the story. So I will be giving you advice in the laboratory regarding safety. And one sort of nuance to this argument that I want to introduce here is the so-called internal resistance. So if you have a voltage source that is in a circuit, the delivery of charged particles, namely electrons, is affected by the mechanism within the voltage source. So if you think about a battery, you have simultaneous oxidation and reduction reactions that are taking place within the galvanic cell. So there's going to be a certain amount of limiting by the charged particle motion through the battery itself. So the ions have to get through the partition between the two compartments on the cell. So that will form an internal resistance, and that will ultimately limit the current delivery through a circuit. So for example, what I'm driving at is if you take that resistor out of the circuit that I've drawn and just short circuit the power supply, in other words, put a conductor attaching the top to the bottom, copper wire, that would be a short circuit. But the current would not obviously go to infinity, because the ions that have to be either the production of charged particles, namely the electrons, that is kinetically limiting. So there's going to be a limited current. You're not going to go to infinity. So this is referred to as the internal resistance of the device. Schematically, I would probably represent it this way. I would just draw a box around the voltage source, and I would distinguish the source, namely the power supply, from the external circuit, namely the load. So this would be like a cartoon type representation. I would embellish that cartoon by including an internal resistance, and then I would revise my Ohm's law for the circuit as indicated on the right-hand side. So the current would be limited by the modified denominator. The power would likewise be limited by the inclusion of that second internal resistance in the denominator. And that concludes part 2 of lecture 1. A few more bibliographic notes included here.